All right, so welcome back, everyone. So today it will be our very last session, and we will be talking about model comparison. So suppose that if you remember what we've discussed in in the earlier lecture, so we have a two-choice learning task. So participants are presented with two-choice options. One is like blue, the other one is yellow, and then they will make a decision. They receive feedback. They will use the feedback to improve their future learning, to improve their future decision making, to gain as much money as possible by the end of the experiment. And we would like to, and we were trying to explain or to approximate the possible or potential cognitive mechanism by fitting the simple reinforcement learning Wagner model. So where we were assuming there is a prediction error calculation. Prediction error means the difference between the expected reward and the actual reward. And we will then also have a learning rate parameter, and that is the important one for us. And after the action values are calculated or computed, we also converted or like translated the action value into action probability. And then the action probability is the most important part of for linking the data to the model, because we can't really directly combine the data and the value. We are trying to combine the data with the probability, because we are using a specific statistical distribution. Here in that case, that is the categorical distribution. So that is more or less we discussed. And we also discussed multiple other stuff, like how to fit multiple participants using a hierarchical version. And also there will be this, there was this model optimization part. But anyway, in many real life cases, real experimental cases, like real life experimental case, scientific procedure, we do not only have one model, we have multiple models. So we will then have to compare and to decide which is the best one that describes our data, right? Because if you remember this this quote, like all the models are wrong, but some of them are helpful. You could also imagine this is like some of the models are better, some of the models are worse, and then there is kind of a scale to position all of the models. So there's a kind of a ranking. And how to do this kind of ranking, how to do model comparison, that will be today's topic. Great. So, model comparison, I'm showing you this one first. I think I should have reversed the order of the slides. So let's say we have some individual data points. So all of these red dots, they are the individual data points, and we would like to fit multiple regression curves. And we fit this higher order polynomial regression. So the order can be zero order, then this is a flat line, and the first order polynomial, that is basically the simple regression with a slope with the intercept. And the second order polynomial, this is the quadratic curve. And then this is the third ordered polynomial, and so on and so forth until the seventh ordered polynomial. So what you can see is like, when the order is low, the model doesn't fit data very well, right? If you see, compare here the dots with the model prediction, there's a huge difference. And if you see like this one, this has the highest number of parameters, or in a way, this is the most complicated one, most complex one. So the more parameters we have, the better we can fit the data. This is the observation here. You see here is all of the data. Red is not a good color here. So all of the data here, they are just basically located exactly on top of the curve, right? There is no discrepancy between the model and the data. Essentially, we could call this 100% precise fitting. But there's a kind of a challenge here. Do you think this is a good model or not? I guess you wouldn't say yes, right? Because this is kind of fitting maybe too well. And we could also imagine that it is fitting well and 100% well only for the current data set. And if in a very ideal world, we only have those data points, then I guess we could be able to choose a seventh order polynomial. But this is not the reality. The reality is that we cannot really exhaust all of the data points. We take samples from a population. And what if we have another data point here? You see here, this discrepancy between the model and the data can't even see the distance, but this will be a large discrepancy between the data and the model. So the new data point is here, and the new data point is here, the new data point is here. So the idea here is like, why do we want to do model fitting? We would also like to make some predictions about some unseen data, some new observations. If we, by whatever reason, have a incoming new data points, let's say that the one that I draw, so the most complicated version, the 7th order polynomial, it cannot be able to fit the new data. Whereas it might be possible be fitted by, like, let's say, for example, this one, or maybe this 4th order. I'm not sure which one is better here. Looks like reasonably better for like 2nd, 3rd, and 4th order, right? So this is the idea. And then why am I talking to you about this? It is because we could imagine that when fitting the model to the data, we have kind of two let's say categories. So the data is composed of signal and noise, right? Plus noise. When we do model fitting, we actually would like to capture the signal, that is kind of the trend of the data, and irrespective of the noise. So if we fit the signal and ignore the noise at the same time, that can be a good one, because that is potentially able to also predict new incoming data points, like additional data points. And if you also fit the signal together with the noise, maybe you are learning too much from the available data. At the same time, it might have a poor performance when there is a new data point income. So then we could be able to look at the previous graph. So here there are essentially two ideas. One is overfitting, learning too much from the data, both the signal and the noise. And the other one, the other extreme, is underfitting, so learn too little from the data. It doesn't really even learn the signal very well, let alone the noise from the data, right? Underfitting is usually not a problem, and overfitting, it is a problem. And we would like to avoid overfitting. So another way to illustrate is like here. This is kind of a famous graph. So we have on the x-axis the model complexity, and then the y-axis the model fit. So model fit is like the average deviance between the dots and the curve on the previous graph. So here, if you look at the line first, as long as we have more parameters, the model complexity can be more or less understood as the number of parameters. So as the number of parameters increases, the goodness of fit also increases. This is kind of a mono increase, right? And the other curve down here is like the more parameters we have at the beginning, the generalizability is also increased, and then later the generalizability decreased. So generalizability here basically means, can we generalize our model fitting to incoming data points? If the model is fitting both the signal and the noise, it is working very well for the current data set, but it's very hard to be generalized to new data points. So then the generalizability decreases at some point. And so for selecting the model, we do not want to compare only the goodness of fit. We would also like to compare the generalizability, right? So here, the model fitting, the goal or the aim is not to find the best fit, only consider the goodness of fit. We also want to consider the generalizability or the complexity of the model. So the model comparison, in essence, or in short, is kind of a balanced idea. So balance between what? Between the model fit and also the model complexity. We want the model fit our data well, but at the same time, we also want our model to be able to generalize to new data points. This is the take-home message from here, I think, model comparison. If anybody asks you what is model comparison, you can just say that model comparison balances or makes the trade-off between complexity and the goodness of fit, rather than the goodness of fit alone. because we might fall into overfitting problems by only looking at the goodness of fit. There might be some other scenarios, like if there are two models, they perform kind of equally well, already considering their complexity. After the complexity is taken into consideration, they are more or less equivalent. And which one do you prefer? So usually there's kind of a principle to say that the simpler one is much preferred, because if two models, one has 5 parameters, the other one has 3 parameters, if they perform equally well, why do you prefer the more complicated one when the 3 parameter model can already explain the variance as well as the 5 parameter model? Right. Questions or make sense? I guess that makes sense. And so conceptually, I guess that makes sense, because conceptually it's quite easy to understand, right? To balance goodness of fit and model complexity. But in reality or in practice, how do we do that? So the best way is actually to do cross-validation. We partition the data. Let's say we have 100 participants or 100 data points, whatever, doesn't matter. And we partition randomly these 100 data points into 5 parts. And each of them, they have like 20 data points. And what we can do is like, we could use the data from the 21st to 100 to do the parameter estimation, and then use this information to predict the remaining 20, like from the 1st to the 20th. Because the data from the 21st to 100, they are used for parameter estimation. When the parameters were estimated, they do not have any information regarding these 20 data points. So this data point, 20 data points, this is unknown. And this reduces the bias, right? Reduces the overfitting problem. And we then could repeat this procedure. So we use the data here together with here to predict this second part. And then we could use the data here and here to predict that, and then so on and so forth. And lastly, we use this one to predict that. So this is called cross-validation, and the white part is kind of called training set or estimation set, and then the other part is called like prediction set or validation set. This looks good, and potentially it is the best practice, but as you could imagine, it takes a lot of time, right? Because you have to do parameter estimation 5 times, and then to do this validation. So also 5 times. And also like partitioning these 100 data points into 5 parts or 5 segments, it is arbitrary decision. And we could, why can't we like partition the data into 20 parts, and each part have 5, right, data points? And also why we just don't say, by not saying that each data point is, it's on itself is a category. So we use data from 1 to 99 to predict this 100, right? We can all do that. All of them are arbitrary. So leave one data set out. And if we do this 100 version, like divided by 100, not divided, like categorized into 100. So then we have to do this cross-validation 100 times. So we do model fitting for 100 times, and we do model prediction 100 times. Simply takes time. It takes a lot of time, and we do not usually want to do that. So especially in this kind of Bayesian parameter estimation framework, one model estimation might take 4 hours, and if you want to do this 100 times, it's 400 hours. That's a lot of time. So that's a lot. So what can we do here in this kind of solution? So we would like to try to estimate the results from cross-validation. So actually, if you have learned from other statistical courses, you have heard about, I guess, AIC and BIC, those are like model comparisons. What are they? They are called information criteria. Yeah, that's good. You heard about that. So what are they used for? Why people come up with these ideas to use information criteria to do model comparison? It is because, as far as I understood it, so all of these information criteria, they are approximations to cross-validation. So cross-validation, let's say this is kind of a good standard, but it takes time practically, and we would like to propose or come up with a few alternative approaches that is more or less resembling this cross-validation, but are faster or more efficient to compute. There are multiple, and AIC and BIC is actually, they are a little bit different conceptually, or kind of philosophically, if you want to call that way. So from the statistical theory perspective. So the rough difference is like, if you really want to understand, usually if you are like taking only the practical perspective, there's not too much need to understand the difference between AIC and the BIC. You can also ask your statistic professors. I guess some of them, they're not very well aware of the difference between AIC and BIC. But anyway, let's assume you really want to go into the detail to know the difference between the AIC and the BIC here. We could imagine like the AIC is try to find out the out of sample predictive accuracy. This is the idea I told you, right? You use the data from 80 data points and then use that to predict the remaining 20 data points. So out of the sample predictive accuracy to predict new data set to see how accurate that is out of sample predictive accuracy. It doesn't really assume that the true model is there. So what do I mean by that? Because this is the assumption of BIC. The BIC really assumes that the true model, the truth of the model is, if you have 5 models, let's say, the BIC is assuming among the 5 models, one of them is the truth. But how do you know that it's the truth? I don't know, right? Maybe you have n models, n plus 1 is the truth. Nobody knows. I guess this is kind of a stronger assumption to do this model comparison. But practically, this doesn't really make so much difference. Usually, they do agree with each other. If you have 5 models, if AIC says second model is the best one, in most of the cases, BIC will also say the second model is the best. Practically, they usually agree with each other. About the conceptual difference, right? Anyway, don't want to lose you. So we are not actually talking about here. We do not talk about that. Because we are using MCMC, Markov chain Monte Carlo, to do Bayesian estimation. When we are doing Bayesian estimation, we do not look at this tool because they are actually related to point estimation, like standard or more classic maximum likelihood estimation, point estimation. Here, because we are doing MCMC, we have a posterior distribution. We have the entire distribution, all of the data points. They carry out information for us to estimate our model, right? So we are taking the Bayesian approach. So when it comes to Bayesian approach, there are at least these two. So the deviance information criteria and the WAIC, the kind of widely applicable information criteria. And there are differences between this. So the BIC is kind of still taking the highest point of the posterior distribution. It doesn't take all of the information, all of the individual data points, whereas the WAIC, it considers the whole or the full posterior when you are evaluating the model. So a lot of talking. So here I'm telling you the take-home message again. Use this one. So this is the best out of the 4 because it takes all of the individual data points on the posterior, which is more reliable and more precise. And this is a good approximation to leave one out. Cross-validation here means leave one out. Right. And so WAIC, this is our target. We use that for comparing models. And the calculation seems a little bit complex. So for completeness, I'm showing you here. Don't even try to understand it. Doesn't matter. We go forward. And what I'm actually want to show you here is like the numeric comparison between or among these a few methods, right? Say leave one out cross-validation. We are assuming this will be a very good standard. We are using 1, 2, 3, these 3 approximations to approximate leave one out cross-validation. And the score is here. Those are the scores. We see that these two are the same. So for at least the simple models, So the WAIC is a very good approximation to leave one out cross-validation, whereas BIC and AIC, they are a little bit off. Most of the cases also precise, but because they're not so much considering the entire posterior, Bayesian posterior. Again, this is to tell you that we use this, okay? We use this WAIC. Questions, if you have? And another practical question is, well, if let's say we have WAIC as a table, we have three models, let's say. So the next question is basically how to order them, which is the first ordered, which is rank first, which is rank second, which is the third. So how to rank it. Here there's a number that says the WAIC is 59.8. What does that mean? Is it good, is it bad, or whatever? So interpreting this number alone doesn't make sense at all, because this model evidence is essentially, they are on this kind of comparison scale. We are only talking about the relative performance. We need to compare which is better, which is worse, but on the absolute scale, that doesn't make any sense. Because one of them can actually be zero, can actually be negative. So maybe let's say one of them is zero. The other one is -2. In a quite extreme case, it's very rare to see negative things here, but anyway, it's possible. And then let's say we have another one, 20, right? We have three numbers, we can order them relatively, because there is a relative ordering, right? The rule is here, to remember that. The rule is here, the lower the better. The lowest is the best. Which is the lowest? This one is the lowest, -2, right? If you want to like visualize it, like 20 is here, 0 is here, and -2 is somewhere here, right? This is the lowest. The lowest, model 2 is the best. This is the rule. So memorize that enough. The AIC, BIC, if you have used that in your other studies, I think you know this, right? So the lower the AIC, the better the model fit. You are choosing the lowest AIC to indicate your best model. So here, this is the same principle. The lower, the better. Now I'm just giving you a short summary of what we've done here. Very simple. We are using something called a WAIC for model comparison because we are doing MCMC. Secondly, what is the rule here? The lower, the better. This is the lowest, then this is the best. This is our take-home message. And this WAIC is already taking into consideration the goodness of fit and the model complexity. So it is already taken care of. So when you are reporting the WAIC score, it is already a balance or a trade-off between the ideas that we talked about, goodness of fit versus complexity. Right. Next question is, good, okay, we know this principle, we know the lower the better, how to calculate it in practice. So it turns out that this is maybe a little bit, I think you might need to watch this again, especially the video from last year. I think there the explanation is a little bit better. So the idea is like, we will have to calculate the log likelihood for the WAIC. It's kind of like this, like follow, let me try to explain you the logic, and then the implementation you can watch or read some other like manuals or references. Let me tell you this. So what we want to have the WAIC for each model. Let's say we have model 1, okay? So the WAIC, how to calculate it? It requires some function with the input of the log likelihood of model 1, okay? Good. I haven't yet explained many things. The function, what function? I'll tell you later. Log likelihood, what is that? This is kind of something that we can understand. So what is a log likelihood? one step above, we are trying to calculate the log likelihood of model 1. That essentially means the log of the likelihood of model 1. Okay, log likelihood, the log of the likelihood. So what is the likelihood of model 1? That is this. If we are still, this is data, sorry, this is theta, this is the likelihood, and how to calculate it. So this essentially equals, let me put here, equals, there's another function to extract our model fit, to extract log likelihood from our model fit. Okay, so we do fitting in the Stan language. This is the fitting results. Oops, this color is hard to see. We do fitting, we have a model fitting result. And after fitting, we call a function to extract the likelihood. In fact, it is already the log likelihood. And when we have the log likelihood available at hand, we input it into another function with the log likelihood as the input argument. Then eventually we will be able to calculate the WASC score. Okay, so this is the logic. And the only thing that we don't know yet is here, this function, how to extract log likelihood, how to calculate WASC. Good, those are the functions that we don't know. We can write it on our spell ourselves, but we don't have to because there is a package called this loop package, leave one out, cross validation, leave one out. Those are the two functions I told you. So first one is this. This is the extract log likelihood function. This is the model fitting. After applying this extraction function, we got the log likelihood. And then we are applying this leave one out function or the WASC function. So here we are talking about this, let's say. And then this will be our WASC score. Okay. If we have a model number 2, we will have a fit 2. We do the above procedures, then we'll be able to for some functions, function 1. Function 2, okay, function 1 means extraction of the log likelihood. Function 2 means the calculation of the WASC. We are able to have 2 WASC scores. Okay, this is how that work practically. And when we have the 2 WASC scores, this is the same thing that I showed you earlier when we have 2 models. Do comparison, right? Now I just give you random numbers, 8 and 50. Okay, so which is better? This one, right? Because this is the lower one among the between the 2. So model 1 is the best. Right. And then this will be just quite relevant to our programming project, because in the programming project, there will be a data set, 1 data set, but 2 models. You do this calculation of WASC and report back to me which one is the best. So which one has the lower WASC. But I will spend some more time talking about that later. For now, let's just try to understand the more important things. Good. Questions? There's something in the chat. Wouldn't it be easy to write a function to directly calculate WASC from the model object? Yes, I guess. I don't know. So this is the package. Because I think maybe I can try to explain this way. So for some occasions, you still need this intermediate step, because some reviewer, like a reviewing process. So if you write a paper and you submit somewhere, and then some reviewer will maybe just ask you, well, what is the log likelihood, and you also have to report that. And so the WASC, you can imagine that this is kind of an end point. So that's the target that we are interested in. But anything that happens in between, perhaps that is more interesting, because if you have the WASC at hand, you can't do much. This is like a relative scale. You can say which is higher, which is worse when you have multiple, when you do have multiple other models together. But if you have only one model, what you can do with WASC? You can't really do anything with WASC, just some arbitrary number. But if you only have one model, you can do a lot with the log likelihood, because with the log too much else. With the log likelihood, you can do many things, like to evaluate like the posterior, and then to evaluate some of the likelihood functions. And then you can also calculate the efficiency of the model. You can really do a lot of things with the log likelihood because that is interpretable. Whereas WASC per se with one model, that's too arbitrary. Good. Any other questions? Right. Yeah. Okay. This you know already. Good. So any other questions? Okay, so I'm giving you a example here, and let's say there is something called a reversal learning task. So what is a reversal learning task? It looks the same as what we have seen. So there are two choice options. You make a decision, you see the outcome. But the reversal learning here means that the reward probability like changes or reverses multiple times. Say in the beginning, the yellow option, the reward probability is 70%, and then it becomes 30%, and then back to 70%, so multiple times. Essentially, the previous version that we've been discussing is a fixed or constant reward probability. The blue is always 0.7 or 0.8, and then the yellow is always like 20 or 30%. It's the same across or throughout the entire experiment. It's pretty easy to learn. Once after maybe 20 or even less, like 15 trials, most people are able to figure out which is the better option, which is worse. But for this reversal learning task, people have to relearn, because if you imagine here, after learning, you establish kind of understanding of which is better, which is worse, but then suddenly the environment has changed. But this changing is not announced to you. You don't know, you can't, the experimenters, they don't tell you that. So you have to learn from establishing new outcome and action contingencies. Right. Anyway, this reversal learning task is a little bit more dynamic, and the participants, they will have to learn and relearn. They have to be motivated to pay extra attention to every detail that is going on in the experiment. Okay, so because the kind of the task structure is nearly the same as what we have before. So what do we have? We have the choices. We have the corresponding outcome of the choices. Can we use the risk-Wagner to fit it? Yes, we can, right? This is almost the same, actually the same, 100% identical in terms of our data file. We have columns: subject, trial, choice, outcome. Whether that is a reversal learning task or the constant learning task, the data file will be identical. And this risk-Wagner is also a good baseline mode to see if that is also able to explain the data from a reversal learning. Kind of a good candidate, makes sense. But on top of that, how can we capture this kind of reversal learning? Risk-Wagner may be good, but can we also find out or come up with another one to improve the standard risk-Wagner? So it turns out that from the literature, I think like more than 15 years ago, like there's a model which is slightly different, kind of a addition to the standard risk-Wagner. Let me tell you what is the difference. So here, this line and then this line, they're the same. Here, prediction error calculation, here the value update, the same as before. And here, the difference is like they call it counterfactual Riskler-Wagner or reinforcement learning. What does that mean? They are like assuming that, so if you are choosing blue and then you get a reward, what would happen if you imagine that in the hypothetical world, if you would have chosen yellow, what you will get? You get a loss, kind of, right? You get a loss. This is the counterfactual thinking. Essentially, you get it opposite, even though that you didn't make that action. But what if you made it? What if you would have taken that decision? Then you will get the opposite outcome, right? It's quite simple, I guess. So just the opposite. So here, what we are calculating is like we are calculating the prediction error of the non-chosen option, even though we didn't choose the yellow. But hypothetically, we are able to imagine that we would have gotten the opposite outcome, which is the opposite of the outcome. So just a minus sign. Practically, this is pretty straightforward. Conceptually, there's kind of some thinking involved, some deliberation. And here, the unchosen prediction error is simply the unchosen outcome, the opposite outcome, minus the value of the unchosen option. And the update also follows the same rule. So the update here, they are just nearly identical. Okay, so only that the chosen value here is updated from the chosen prediction error. The unchosen value is updated from the unchosen prediction error. This is the same. And they are using the same learning rate. You might imagine, or you might be wondering why the same learning rate is for simplicity. You can't have two, it's possible. Then there you have another model, right? So we could say that model 1 is Riskler-Wagner. Model 2, let's call it counterfactual Riskler-Wagner. And then we have model 3, counterfactual Riskler-Wagner, 2 learning rate. So one learning rate for the factual updates, another learning rate for the counterfactual update. You have the 3 models. And what you can do next, write down your model in the Stan language, do the fitting and extract log likelihood, compute WASC, find out which is the lowest, that one will be the best model. So this kind of a workflow when you are having this kind of data at hand, what you're supposed to do, you do what I told you. Right. And say if you are doing this thing and you are like comparing the model, yeah, this is how the model works. If you are comparing the model, and then there will be some fancy plotting, and I will skip this for now. And then later on, if you run this analysis, you will be able to see this WASC or the Lu score. Okay, you could either use the Lu or the WASC here, because both of them they are implemented in the Lu package. So for each of these outputs, we have a table here. The structure looks the same. We are looking at the last line of that table, which is here and here, right? Those are there. These 2 numbers are the values that we will be comparing. So one of them is 779.5, the other one is 562.6. So which is lower? It's quite apparent, right? This is lower. So this is our best model. Okay, good. Model comparison finished. Questions? So there's a question in the chat in the prior side. What do you do if there is more than just one other unchosen option? Could you perhaps give the different options different weights, each depending on how likely they are? Yeah, this is a very good question. Very good. So here, this model, let me explain this. We have a reversal learning. It is part of the experiment that if you choose blue, you get a reward, and if you choose yellow, then you don't get a reward. You have this is called complementary outcome. If you get a reward, then you are sure that if you would have chosen the opposites, you will get the opposites. It can be the case that the two options are independent. So blue and yellow on one trial, it's possible that you get both a reward. It's possible that you get this. It's possible you get that. It's possible that you don't get anything for choosing any of them. This is called independence reward structure. This is called I don't want to write this too long, complementary reward structure. The counterfactual learning model only works when you have a complementary reward structure, because you know you would have gotten the opposite. Here you have no way to know the opposite because that's too much. So for the dependent reward structure, that counterfactual, I would assume that it wouldn't be better than the standard rich Wagner, because you're basically learning nothing from the counterfactual part. Right. But this, I guess, doesn't answer your question yet. So you are saying if there are three options, right? Say I have a blue option, and I have a yellow option. I have another one, what's red option. I have three choice options to be chosen from. So on the screen there are three. And then if you choose this, yes, you choose this, and you get a reward, good. Standard rich Wagner will work here without any problem. So because as we discussed multiple times, as long as you have a action reward structure, you are more than guaranteed to estimate a rich Wagner model for that cases. So here we have three options. What to do? Can we use the counterfactual thinking? Again, it's kind of relies on the task. First of all, in most of the cases, if there are three choice options, it will be very likely to have an independent reward structure. So this is already indication to say that counterfactual model maybe doesn't work, maybe won't work. But what if there is a there is a complementary reward structure? But how to complement this? I don't even know. One is okay. Let's do this. Say among the three options on each trial, only one of them will lead to a reward. And if you would have chosen either of them, you get a loss. Okay, I guess this is possible. Yeah, so it really depends on your experimental design and how you would like to deliver your outcome. So complementary always implies a binary choice or something. No, I guess this is also kind of complementary, right? One is a reward and the other two are like nothing, up or loss. Okay. Good. And questions? There's another one in the chat. So you can do a reward, nothing, and loss model, right? Yes. It depends on your design, depends on your model. So I think I think I didn't mention this idea yet. So we are like in the more general field of computational neuroscience or computational cognitive neuroscience. Whenever you go to a conference or you present a paper, you write an article, and then there will be the reviewer, right? We talk about that multiple times. It's really easy to ask a question to ask the person who is presenting the work or who is writing the paper. It's very easy to ask them that, have you considered this? Have you considered that? Do you have another model where you consider reward, loss, and nothing? It's very easy to ask, but how to properly answer this question? If let's say you are the author of the paper, how do you defend yourself, or how do you convince the other people who are asking you this question? So I think you can think about this for 5 seconds. So how would you best, or maybe tell me, any of you have any ideas? So if you are presenting a work, you have done amazing analysis and everything's very thoughtfully considered and carefully analyzed. And then I go to your poster or talk and they say, hey, brilliant talk, but have you considered this and that? Can this be another model? Have you tested this version, that version? So kind of this kind of question. How do you best respond? What's your best response? Okay, so there's a response in the chat from Annika. So I would say try to apply a freely interpreted version of, okay, of this outcomes razor to my research. Yeah, so when in doubt, use the simpler method model. Yeah, okay. So if you are responding in this way in the conference chat in the poster presentation session, I guess people will be fine and then they will be convinced. But what if the reviewer say that, yes, I understand. Thank you for this response. Outcomes razor is possible in these cases, but still I would like to see the results of you implementing the model that I have in mind. It's very difficult to argue by words. The best approach is actually just run it. You really just run it. Yeah. If that is better, you thank the reviewer or the people who are asking the question. If that is not working, if that is not better, you have the evidence. You say that, hey, good question, good suggestion. I tried, but that doesn't beat my current best model. This is the way more convincing approach. The drawback is obviously it takes time, right? Because as I said, you are about to submit your paper to a journal. It's like your project is nearly finished. And then there's a guy very annoying asking you, can you do this additional analysis? You are a little bit reluctant to do it. So you have to take the balance. You have to take the balance of it. Maybe you can just submit it either way. But if that is a review comment, you do have to take it seriously. So just run the analysis. Good. So the message, let's get back to this lecture thing. So the message I want to tell here is like, whenever you are trying to like ask a question either to other people or yourself, when we are doing this cognitive computational science thing, we can simply just run it. So whenever you think, is that possible? You can try to convince yourself conceptually or theoretically. Maybe that's possible, maybe that's not. But as soon as you are convinced by yourself to say, maybe this is possible, but I'm not sure if that is better or worse, what to do? Just do it. You have to implement the model. Because in most of the cases, you have model 1, 2, 3, 4, and your additional idea will be just a slight adjustment to your current best model. And then you run it, wait for maybe just 1, 2, 3 hours or the next morning. Then come back, and then you know whether it's an improvement or not. Both way, either way, they're good for science. They are good scientific practices. Make sense? This is at least what I do. So if there are people asking me, I just run it. That is way more convincing. Great. Okay, there's a small thing. So this is posterior predictive check. This will not be part of the programming project that you will be running. So the idea is like this. I think we mentioned this also maybe in the other video that you watched. So we want to know that model comparison. So we have 1, 2, 3, right? Model comparison tells us which is the best, but is this really a good one? So we know the relative performance. This is the best, this is the second, this is the third, okay, whatever. But what if the best one is still kind of predicting the data only 60% of the variance or 60% of the accuracy? So on the absolute scale, even the best among the 3 is still kind of a poor guy. And we have to do another step to validate our model, to validate if our winning model is a good model. So how to do that? We want to go back to our posterior predictive check. So we would like to use the posterior distributions to generate fake data from our distribution, and then to compare if the model simulated choice would resemble the actual pattern of the data. If they match up, very good, the model can be validated. If there is some discrepancy, you might want to improve your model until you're happy with the performance. Say here we have the kind of dots. So this kind of dots, you can see that all of them are real data. They are the real data. There's a curve. And we have two models. One is the Risk-Lavagna, the other one is the counterfactual double updating Risk-Lavagna. And roughly, so both of the two curves, they follow the pattern of the data, but you can see quite easily here is like the variance of the red one is smaller than the variance of the blue one. So the red one is narrower than the blue one, which also means the red one is more precise than the blue one. Like qualitatively, they both look fine, but qualitatively, the red one has smaller variance. And we could also do it another way, like the blue line here, this is the real data. And we are comparing the model simulated choices from the two models. One is from the red and the other one is from the blue. And you can see that the real data here is centered around the red one. Is at the central location of the red distribution, but not the central location of the blue distribution, which indicates that the red one is better than the blue one. So this is like a posterior predictive check. That makes sense? So posterior predictive check is like this, maybe another explanation. So if you remember, like from regression line, those are just dots, individual dots, you fit a line here. And you would like to generate predictions from your regression line. And if your regression line is kind of like, this is like shaded area in the imaginable world, fix that in your head. So if this shaded area is covering this real data, let's say 95% of the time, this is kind of good model, right? So if this is the individual data points, kind of this way, a little bit curvature, and if you fit a line, and then this is the shaded area, it doesn't even follow the pattern, right? The pattern might be like this, and you are fitting another one, a straight line, and then this doesn't match. So the posterior prediction check works for every single model. It can be a statistical model, regression line, or like here, choice model. Either way, they should work. Good. So is this still a comparison, right? What arbitrary criteria are there? Say the best model predicts well enough. Yeah. Okay, good question. So what we can do is like this. Say in this graph, we have, let's say this is the real data. And then we say, well, this is kind of the model, right? There are two variables, X and Y. So you do a correlation, that is fine. So if they follow up, if the model follows the data very well, let's imagine the correlation coefficient R equals 0.99. Very good. This is a good one. But what I'm trying to say is like, if we have models 1, 2, 3, 1, 2, 3, if this one is the best one according to model comparison, which is on a relative scale, what if the correlation coefficient between the model prediction and the data is still not so ideal, for example, 0.65, and we still have room to improve the model performance until we are happy, for example, here. And your question, I guess, is how do you know you're happy? This is it's also no cutoff. I don't know. You could say that 0.9 correlation coefficient is good enough. 0.65 is not. So it's kind of the from experience, like from some kind of like experiential cutoffs, like 0.3 is low correlation coefficient, between 0.3 and 0.6, between 0.3 and 0.7 maybe okay-ish correlation, and anything between 0.8 and 0.99 or 1.0, it's strong correlation. Yeah. Another question is explain the counterfactual again. Yes. It's like, so if you choose blue, you get a reward. And in the hypothetical world, if you would have chosen yellow, you will get the opposite, right? So this is the counterfactual. You are like trying to understand what is the counterfactual outcome if you would have chosen the opposite. And this happens or applies to both ways. If you choose the blue, you get a loss. Then you also will know that if you would have chosen yellow, you will get a positive outcome. So this is kind of the counterfactual thinking or counterfactual updates. Does that make sense, Roman? Yeah, cool. Right. So this kind of debugging thing, this is your, you need to watch it afterwards. We really don't have time for that. So let me finish this and then I'll stop the recording. Let me first try to summarize this a little bit, and then we can have more time for like the homework thing. Right, very short. I will try to be short. So we, at the beginning of the semester, like March, right? So we are like introducing the R and R Studio as the platform that we will be working on. And then we talk about probability. Always memorize that there will always be the differentiation between the discrete events and the continuous events, probability mass function versus probability density function. And when we are talking about density functions, we have like the PDF and the CDF, the probability density and the cumulative density. And then we talk about the Bayes rule and how did we end up with the Bayes rule? It is because we have multiple events. We have the events A and B, and we have joint probability, conditional probability, and the marginal probability. And then the Bayes rule is essentially describing the relationship between like the probabilities of multiple events. And the probability of A given B here is helpful, but it's not so interesting because we are trying to do data analysis. We replace A and B with something more informative or interesting, which are data and the parameter. So here we rewrite the Bayes rule with theta and the data instead of A and B, and we call them these ones the probability of theta given data, the posterior. So this is our target. We want to know what the distribution of our parameter looks like after we have observed our data, the posterior after the data observation. And this one, according to Bayes rule, is equivalent or is equal to in the denominator, the product between the prior and the likelihood, and then this is divided by P of D, which is a normalizing term. So then we entered into a quite concrete example. It's kind of the same as the coin flipping example. We want to know whether the coin is biased, and we throw the coin up into the air, we catch it to see if there is a head or a tail. We have binary observation, head, tail, and there's unknown probability of the height, probability of head facing up. And so we do experiment and we observe the head, tail observations, and we use a Bernoulli distribution to model this process. And remember that we are always trying to link the known data and the unknown parameter also with a proper likelihood function. The likelihood function here, that is the Bernoulli and the binomial and the Bernoulli. And later we also had the likelihood function of a normal and also the categorical distribution for our choice data with Wagner. Estimating the posteriors for a simple model with only one parameter, that is quite straightforward. We can use grid approximation or grid search. We don't even have to run MCMC, Markov-Chain Monte Carlo, but why we do have to run MCMC, it is because for complex models or for hierarchical models, we can't even solve the problem using analytical solution, using a grid approximation. Some of the likelihood function, you don't even know the shape. There is no shape. But how would you do that? Is that still possible to be estimated, the posterior? It is possible using sampling approach. We try to draw samples from the parameter space, the parameter geometry, and then we use the sample. Remember the idea of the MCMC robots, there is a kind of mountain. The robot wants to know, well, we want to know where the mountain is high, where the mountain that is low. We send out MCMC robots. The MCMC robot doesn't have vision, but it has elevation sensor. It can tell where is high, where is low and then the MC robot also makes proposals and then moves up or climbs up. And using these frequencies of location information, we are able to approximate the shape of the mountain or the shape of the parameter geometry. Right. And then we moved on to the second big part, which is the cognitive models. So the cognitive modeling idea is never new to the entire scientific world. It might be new to cognitive science, might be new to cognitive neuroscience, but it is never new to science because like a few hundreds of years ago, like physicists, they are trying to understand how like planets travels around the sun or how the satellites travels around the planet, like the moon, for example. So the process here is not physical, it is mental or cognitive. And we are trying to understand what is a cognitive process when individuals are performing some cognitive tasks. For example, learning, for example, decision-making, for example, reinforcement learning. This is one of the most helpful and quite straightforward and influential model in the field. It is used a lot, and there are classic paper from nearly 20 years ago. There are also new recent paper from this last year. It is still developing, and this is a very interesting field. Then we implemented our model into this hierarchical fashion in terms of combining two levels. One is the group level distribution, where we assume individuals have a common source. So they are sampled, they belong to a common population, and they do also retain their individual differences. The combination of the group together with the individual fitting, so it is called a hierarchical fitting. Hierarchies or multi-level fitting, which is more precise and more reliable, and will give us better results than the more classic maximum likelihood estimation. So lastly, then we have talked about the optimization of the STAN language. It is because sometimes the direct translation from the equation to the code, as if you are translating from German to English, the direct translation, the first attempt might not be so ideal. It makes sense, but there are better ways to improve it. So here we would also like to improve how we could code a STAN model from math. And just a few seconds ago, we talked about the model comparison, because in many cases, we don't have only one model, we have multiple, and we have to decide which is better, which is worse. But deciding which is better, which is worse is not the final step. We also have to evaluate or validate on the absolute scale. Is the model really good? Is that a really good one? So then what we do posterior predictive check. So after the model fitting, we generate fake choices, fake data from the posterior, and then compare if the pattern of the simulated data could match up the pattern of the real data. So like the correlation idea, just to draw. Great, debugging, I leave this to you to watch, and then there are some other advanced topics. If you don't really work on fMRI, I guess I can skip this. The material is there, you can just take a look afterwards. Right. So this is kind of a table of the summary of what we have on GitHub. All of the materials are there, all of this information are there. And if you have taken the, if you follow me, I think from the beginning to the end, I hope that you have at least a conceptual understanding of what cognitive modeling is about and how that can be useful. And if you would like to take in or deepen this practice or like deepen understanding, always practice makes perfect to really just code it on yourself. This is what I mean. And this is kind of a comic. So from this website, or interesting, you can, if you do research, sometimes spending time, you can spend a whole afternoon here to look at the funny comics. So here on the left-hand side, like doing research is about 90% of the time to work and 10% of the time you really had a kind of result. You have to debug, you have to clean the data, you have to discuss with others, and then you really have a meaningful result. But conversely, when you are writing about it, this pattern reversed. So you will spend like only 10%. This is the method section, talking about what you did. And then 90% of the time writing about the results. So it's an interesting part. And another thing that I want to talk is like, well, this modeling in STEM language, this is a new language. The new language is how new? I think still less than 10 years. That is a new language still. I would rather call that a new language. Python is even older. So Python is older. If that is too new to the field, it falls into the challenge that not many people know how to use it. So then I'm here to teach you, but maybe this is still too much. I really understand that if what I'm talking about the whole semester is perhaps a little bit or maybe too overwhelming. But the good news is that there are packages available. So a few years back, and we realized that coding the STEM model, coding the decision learning models in the STEM language is challenging, and why not we just code it for the community and the people can just use it. The way I'm teaching you is bottom up. We really try to open a empty script, code it from bottom up, from scratch. But there are things that is already coded, so you can actually follow everything. Great. And then the package has many things, and as you can just take a look, it has quite a lot of downloads so far. And later on, if you really want to go forward, what is next? You can take a few more summer schools. And there are like multiple, and so in Europe and in the US, many of them, they are actually free, so, or with a very little cost. Yeah, the references, and then some of the people I want to thank, because along the way they help the development of the course materials, and I wish you a happy computing.